In this video, I want to talk about the Pauli operators, or the Pauli matrices, and discuss why they're so important in quantum computing and quantum mechanics. So the Pauli matrices is a set of three different matrices: sigma x, sigma y, and sigma z, where sigma x is equal to the following. Sigma y and finally sigma z. So what makes these matrices so important, so special? Well, up until now, we've mentioned two kinds of special linear transformations that we can work with in quantum computing. One is unitary matrices. And remember, unitary matrix U has the property that U dagger times U is equal to the identity is equal to U dagger. And we also talked about Hermitian matrices. And recall that our Hermitian matrix H is equal to H dagger. And this is a different requirement than unitarity. So just know that these two things are different. And a consequence of this definition for Hermitian matrices allows us to build up a nice mathematical formalism for observables in quantum mechanics and things that we can measure. So remember, Hermitian operators correspond to observables. Namely, their eigenstates are the different states that you can find a quantum bit to be in this case. Now, the thing about these Pauli matrices is that they're all unitary and they're all Hermitian. So not only do they represent real physical transformations we can make to the qubits, but their eigenstates correspond to different states that we can measure qubits to be in. And finally, a third property of these Pauli matrices is that they're all linearly independent from one another. So you cannot express any of these Pauli matrices as a scalar multiple of another. Now, say you're working in some vector space with d dimensions. So every vector has d elements. If you're able to find d different linearly independent vectors, then those vectors, that set of vectors, can form a basis for your entire space, which means that any vector with d elements can be expressed as some linear combination of your basis set. And now we can think of 2x2 matrices as four-dimensional vectors. And the reason for that is because, at least when it comes to taking linear combinations, the rules are exactly the same. If you want to add two vectors, let's say A, B, C, D, and E, F, G, H, the rules for addition are A plus E, B plus F, and C plus G, and D plus H. Now, what if you wanted to add together two matrices? Well, the rules for matrix addition are exactly the same as the rules for vector addition. You just add each element. And D plus H. And not only that, but scalar multiplication is exactly the same too. Whatever scalar you're multiplying by, every element in either your vector or matrix gets multiplied by that scalar. So this idea of spanning an entire space with some set of vectors or matrices works for both vectors and matrices. Now, that would mean that a 2x2 matrix space is, in this idea of linear combinations, is kind of equivalent to a four-dimensional vector space. And we already have three linearly independent matrices to work with. So if we tack on a fourth, we can tack on the identity, which happens to also be unitary and Hermitian, and linearly independent from all the Pauli vectors, or Pauli matrices, then we can form a basis for all the 2x2 Hermitian matrices. And that's kind of amazing, because what that means is this set, consisting of our Pauli matrices, along with the identity, spans the entire space of observables. So any kind of measurement that you would make on a quantum system is going to collapse your quantum system to a state that can be expressed as a linear combination of the eigenstates of any of these matrices in this set. So we can build up any kind of measurement device we'd want out of these Hermitian operators in the identity matrix. And this is what makes the Pauli matrices so fundamental in quantum mechanics and quantum computing. And before I end this video, let me just, I just said that we can express any two-level quantum system as a linear combination of the eigenstates of the operators in this set. And because of that, this gives us a nice, very intuitive way to think about a two-level quantum system. We can imagine that we have three axes in 3 dimensions, and each axis corresponds to one of these bases. So we could have a z-axis, x-axis, and a y-axis. And we can also draw the other end of the spectrum here, because each of these each of these operators have 2 eigenstates in them. So you can imagine at any point in time, you have this sphere. You have this sphere of possible states that your qubit can be in. And if you make a measurement, it's going to collapse to one of the states on the boundary here. So spin up in the z direction, for example, will give you this. Your qubit will be on this spot, right? And then spin down in the z direction will be in this spot. And likewise for spin up and spin down in the x and y directions. And at any given moment in time, your qubit can be represented as kind of a vector on this sphere, where its endpoint is on the surface of the sphere, lying in between any of these these eigenstates, or the points that represent these eigenstates. So we have these pure quantum systems, these two-level quantum systems, and we can neatly visualize actually what's happening to them as they evolve. And this sort of visualization, this sphere right here, is called a Bloch sphere. And try not to let it confuse you too much, but essentially it's just a nice way of visualizing a two-level quantum system. And this will show up a bit in this series, so I thought it'd be nice to bring it up here. And before I end the video, I just want to show you guys, because I said that these are all unitary transformations, all of these Pauli operators, that we can actually apply these to our qubits and see how they change the qubits. And I think the most enlightening one right now is to look at the Pauli X operator and see what it does to our computational basis, for example. So we could have some qubit in the 0 state, and let's say we want to apply this Pauli X operator. Well, this is going to give us the matrix that is represented by this operator, and then 0 in the computational basis, and you can quickly see that it sort of flips our qubit. It gives us a 1 in the computational basis, and likewise, this is going to give us 0. So this Pauli X operator is the sort of quantum analog to a logical NOT gate. And now you can see how we start to build up these logical operations that we can make on qubits, but in a quantum setting. And finally, in the next few videos, I'm going to introduce the oracle model of computation, which is the basic mathematical formalism that we use to look at and analyze quantum algorithms. and we're going to demonstrate some very interesting speedups that you get by allowing for quantum interference and quantum entanglement, which I still haven't talked about. So I'll see you in the next